Good afternoon, everyone. I'm Saruna Kunwar. I'm a PhD student at Laurentian University in Sudbury, Canada. It looks like I'm the only one student presenter here. And I was also asked to have only 2 slides for the presentation, so I have only 2 slides. I hope that will not be so boring for you. And the topic I'm talking will, I hope it will be new and interesting for you all. I'm funded by Miracle and SEMI in Sudbury, Canada, which are the mining innovation companies. I'm in the group of energy, renewables, and carbon management ERCM group. Today I'll talk on what my PhD research is all about and how I will be working on it. So I'll be talking on using wind energy to produce cryogens for use in deep mine cooling and ventilation, which is also my PhD project. This project we have given the name Cryovent from the cryogens and its application for the ventilation in underground mines. The project is about producing cryogens for use in deep mine cooling and ventilation. A cryogen is a gas or air which has a boiling point at atmospheric pressure below around minus 150 degrees centigrade or even lower. They can be used in many applications of gases. Many applications in different areas such as in milling, smelting, liquefaction and separation of gases, cryogenic surgery and low temperature chemical processes. Examples of such cryogens are liquid air, liquid oxygen, liquid nitrogen, liquid helium, and so on. Cryogens can be produced in various ways, but I'll be talking more about liquefying gases, especially air, atmospheric air, using wind energy and their application in deep mines. The Cryovent project is motivated by the exhaustion of world-class surface mineral ore bodies and the consequent need to exploit deeper ore bodies exploited using underground mining methods. Also, ore bodies that are already exploited using underground mining methods are extending workings deeper, and therefore the working environment for both workers and machinery is becoming hotter. At 3,000 meters depth, the temperature of air entering ore producing areas may be 20 degrees centigrade to 30 degrees centigrade higher than the surface air temperature, mostly due to adiabatic autocompression in the confined environment of an air shaft. Ventilation air mass flow rates are of order of 1 tons per second in medium to large scale producing underground mines. At these depths, where the virgin rock temperatures exceed 50 degrees centigrade in most mining areas, geothermal heat transfers will further increase the air temperature. The principal desired characteristic of an alternative cooling method is thus that it should deliver cooling cheaply. Load factors of current refrigerating plants in underground mines are approaching infinity with the greater depth, so the cooling needs to be provided continuously. This means that the capital costs of cooling plants, either conventional or alternative, are less important than the operating and energy input costs. This suggests that the use of a renewable energy source such as wind energy to provide cooling, because the input energy costs are close to zero. With this project, we propose that the production of liquefied air using wind energy may be a suitable solution to the problem of providing cooling to deep mines. Wind turbines are the most mature and largest scale technology that harness renewable energy. If configured for the production of liquefied air rather than electricity, the traditional difficulties of integrating wind energy into electricity distribution grids are avoided altogether. The cooling can also be stored in the form of the condensed liquid, and the storage, distribution, and transportation of cryogens at bulk scales also use established mature technologies. What is shown in the figure is the schematic of the proposed concept, which we have given the name of cryogenic. Proposed concept is to integrate wind energy capture with a cryogenic production system, which is also called the Linde-Hampson liquefaction cycle, which produces cryogenic also, which examples I gave were the liquid air, liquid oxygen, nitrogen, and so on. The Linde-Hampson cycle, as shown in the figure, is integrated with the variable speed rotor wind turbine. The air liquefaction cycle, called the Linde-Hampson cycle, was developed by Carl von Linde and William Hampson independently in 1895. So these cycles are being in use for more than 100 years. In this cycle, atmospheric air is first compressed with a pressure ratio typically around 200 or even more, and then passed through the heat exchangers, as you can also see in the figure here. This is the compressor. I'm only talking about the Linde-Hampson cycle first. This is the compressor. The atmospheric air is taken from here inside the compressor, and then it goes through the heat exchangers, the aftercooler and the cryogenic main heat exchanger, and then it is passed through the expansion valve. The expansion valve can also be replaced with the expansion turbine. The high pressure and temperature atmospheric air is allowed to expand here, and then it is passed through the lower vessel in which it becomes liquid air. The remaining air, which cannot be liquefied, is passed through the cryogenic heat exchanger again, and then to the compressor, completing the cycle. And it is also used to cool the atmospheric air intake again. The rotational and torque developed by a wind turbine rotor can be highly variable, and so the key question to my research is whether liquefied air would be as efficiently produced with the variable speed wind rotor, because the Linde-Hampson cycle is always being done by using electricity with constant input. In order to buffer the intermittency and variability of the wind energy in the very short term, an open-loop hydrostatic transmission could be deployed, as shown in the figure. This is the open-loop hydrostatic transmission, which is used to integrate, to link the variable speed wind rotor and then with the compressor of the Linde-Hampson cycle. So the system would consist of a positive displacement hydraulic pump, a hydraulic motor, required control valves, pipes, pressurized and non-pressurized reservoirs, and fittings. The motor is driven by pressurized fluid drawn from an accumulating reservoir replenished by the pump. Thus, the hydrostatic transmission can also be used to adjust and regulate wind rotor speed, and the rotor blade tip speed ratio can be regulated to maximize efficiency over varying wind speeds. The fluid coupling of the wind rotor to the compressor is a form of torque converter equipped with energy storage. In this slide, I have the application of the cryogenics produced using wind energy for the underground. Converting wind energy into a cryogen that can be reboiled with environmental heat, thus the ambient heat, creates a readily stored and transportable form of energy, an energy vector that can also be used for mine spot cooling, as shown in the figure. There are different integration technologies for electricity or cooling effect generation using wind energy. In the paper I've written here, I have discussed about 7 different integration options, and those are compared with each other and also with the proposed private project, which is my PhD project. Concept in terms of capital cost as well. The annualized costs are also calculated with some assumptions, and the references are available in the paper. Overall efficiencies and the capital costs of each system are also calculated. All the required references are cited in the paper. going to talk about three different options of integration and their costs for delivering cool mine air. The proposed dry vent concept for delivering cool mine air is calculated to be around 18.27% efficient with total capital cost of around $2,700 per kilowatt, but providing some cooling as well at the same time. The annualized cost for this system would be around $7,900 per year with zero input energy cost. The same concept would cost, the annualized cost for the same concept would be around $6,958 per year if it uses electricity to run the system with an annual input energy cost of $2,499 per year. The conventional vapor compression refrigeration plant, which is usually used in the underground mines for cooling and ventilation, which is run by the electricity grid, would be around 86% efficient with around $900 per kilowatt total capital cost, providing the same amount of cooling as the proposed private project. But the annualized cost for this system would be around $6,963 per year with an annual input energy cost of around $3,796 Canadian dollars per year. So the application of the liquid air produced by using wind energy is shown in the figure. Liquid air produced in this manner using wind energy can be used for various purposes, but the motivation for the development of this concept comes from the need of high volume ventilating air in the deep mines. With the available natural resources being depleted in the surface, the global mining industries are acquiring the underground concept to increase the mine operation life by some additional years. The fact that the autocompression and the geothermal gradient only add heat to the prevailing hot temperature in the underground mine working area is putting the mining industries in a constraint of having an efficient and cost-effective way for deep mine cooling and ventilation. Liquid air can be delivered underground with the help of small diameter boreholes as shown in the figure. In this figure, you can see the intended application area for the deep mines. The liquid air is generated from the Laurentian wind turbine, which is stored in a storage tank and then delivered to the subsurface via a borehole. Liquid air also evaporates by mixing with the subsurface ventilating air, thereby cooling it at the point of use. This project also mitigates the problems with the storage of the wind energy because when wind energy is converted to the liquid air, it can be stored very compactly because it will be very less in volume when it is liquefied, when air is liquefied. 1 kg of liquefied air at atmospheric temperature stores around 440 kilojoules of cooling at around -200 degrees C. That would be recovered through reboiling using the heat within ambient mine ventilation air at 30 degrees C. 1 cubic meter of liquefied air effectively stores 400 megajoules of cooling for the same conditions. Once the cryogens are produced, they can be stored in an insulated vessel at atmospheric pressure and then transported easily. If they are produced offshore and need to be stored onshore for electricity generation later, they can be delivered onshore with no extra cost except the pumping cost. The energy density of cryogens is around 20 times higher than that of compressed air energy storage. Cooling loss with cryogens stored in a Dewar vessel, which is just the insulated vessel, is principally by heat dissipation, which is only around 1% per day. The use of cryogens that can be delivered by a borehole from surface to the subsurface will eliminate the need of huge ventilation shafts. Cryogens also provide bulk cooling to the ventilating air during expansion. Though liquid liquefying air is costly. The initial installment cost of such plant is offset with the two major benefits of using cryogens as compared to the conventional ventilation method for the deep underground mines, which are the low-cost electricity and the additional benefit of cooling. Therefore, on the long run, the proposed concept of producing cryogens with the use of wind energy, storing the surplus production, and using them on demand for the mine cooling and ventilation can be a promising way to minimize the energy costs in mine operations. Now, for the conclusions, I have the Linhausen plant and other plants producing cryogens have been designed to operate with continuous and steady power input for the compressors for many years. But our project Cryovent aims at liquefying gases from the variable input of wind energy. It is a cost-effective and efficient way to cool and ventilate the deep mine air by liquefaction of gases. And the use of renewable sources of energy, such as wind energy, makes it more environment-friendly. This is all I have to share on my research, and if you have any questions, we can discuss it about later.